Okay, so here's a recording of the lecture that goes along with section 3.1 about the derivative of a function. We start with this idea that we have this definition of the derivative function, that the derivative function is the limit as h approaches 0 of f of x plus h minus f of x all over h, provided that the limit exists. We'll talk more about that part later. But let's see if we can go into the details of those symbols and figure out what all this means. So let's say I have some function. Here's a function. Try doing that again. There's a. There we go. Stuck that time. And let's say I'm interested in what is the tangent line slope for that particular point. And I'm like, okay, well, I don't know what the tangent line slope is, but I do know that if I choose another point on the curve, I can find a secant line slope. Okay, and then maybe I start labeling some things on this graph. Let's call this point x, and the red point, therefore, is x comma f of x. Let's call the distance from x to this point h, making this x coordinate x plus h, and the coordinate overall for that point as x plus h comma f of x plus h. Now, if I want to find the slope of the secant line, I would look at the differences in those two y values, f of x plus h and f of x, and divide it by the differences in the x values. X plus h is one x value, and x is the other x value. And that's great. That's the slope of the secant. And what I'm saying is the secant is an estimate of the tangent line slope. It's an estimate. Okay, is it a good estimate? Well, let's go to a demo. On this calculator, I have a function, and the function is drawn in blue. I have a secant line, which is drawn in red, and I have this little slider here, which allows me to move those points closer to each other. Let me do this. Go here. And let me just make sure my settings are good. So size is 0.01. Great. Okay. So when I move this slider, I can move it very, very discreetly. Until I can get those 2 points really, really close. And when I do so, the closer I get, the better the estimate is to the slope. So when they're almost on top of each other, it looks like that slope is hanging right around 2. Okay? Well, that's me playing around with numbers. Can I play around with symbols? Sure. I could say that the secant line slope, after I just do a little cleaning up here, this x and that x cancel, I could say that the secant line slope of f of x plus h minus f of x all over h becomes better and better estimator of the tangent line slope when the distance between the 2 points gets smaller and smaller, i.e. when h approaches 0. And that's our definition. we're going to get slopes out of this limit expression, and they're going to be not just good estimators of these tangent line slopes, they're going to be perfect estimators of the tangent line slope. Which brings up an idea. We declare this to be a function called f prime. But why f prime? Well, it's because it is a derivative of f. What does that mean? Well, derivatives, like derivative works, come from another work. Okay? Or if we were to think about maybe a reflection of a triangle across the line, the point that gets created gets the mark a prime because it came from a. So I'm talking about a new function, and it came from the function f. It's going to be dependent on what function f is doing. So, for example, go right down to this example here. Can we find a function that's going to give us all the slopes for the curve x squared? Well, according to our definition, the function that gives us all those slopes, f prime, is the limit as h approaches 0 of, by definition, f of x plus h minus f of x all over h. But in this particular instance, the function is the squared function. So I'll square both of our functions. If I expand the top, I get x plus 2xh plus h squared. Sorry, there's x squared there. Minus x squared all over h. Those x squareds cancel. Giving me the opportunity to take an h out of both of the terms in the numerator. These h's cancel, which allows me to apply the limit, and I'm left with 2x. Let's see if we can summarize. If f of x is x squared, then the derivative function, the function that comes from that x squared function, that returns us the slopes, is 2x. Okay, let's try this out. Let's talk about what's going on at 1. At 1, f of x, f of 1 is equal to 1. F prime of 1 is equal to 2. Okay, well, so does it look like when I'm at 1 that the slope of that tangent line at that location has a slope of 2? Yeah, it looks like it's possible. How about f of 0? Well, f of 0 is equal to 0. F prime of 0 is 2 times 0, which is 0. Let's see. Does that make sense? Here's f of 0. Does it look like its tangent line slope is a horizontal line with slope 0? Sure does to me. Okay, last one. How about f of negative 1? Well, f of negative 1 is negative 1 squared, which is 1, which places us out there on our graph. F prime of negative 1 is 2 times negative 1, which is negative 2. Does it look like this has a slope of negative 2? Does to me. Now, you see that our original function is a function. F prime also acts like a function, right? So if it's a function, we have to discuss its range and domain. We do know that the domain of the f prime function is going to be the same or smaller than the f function. And wherever we say that the derivative f prime exists, we say that the original function is differentiable, or it has a derivative at that location. Now, this definition, the one that we started off with, what I call the H definition, It's good. It's clearly showing the slopes, but it's not the only way we can get at the slopes. Here's an alternate definition called the A version of the definition. It says, hey, you want to find the derivative function at some location A? Well, you can think of this as f of x minus f of a all over x minus a, and then just think about, again, the 2 points getting closer, x getting closer to a. Let's draw out what that looks like. So here's an x and a y axis. Here is some function. Let's say here is the point that I want to find the tangent line slope. It looks like that. Here is a point that I can draw a secant line. Let's do some labeling here. Let's call this point A. Let's call this point X. So this is the point A, f of A. This is the point X, f of X. And the slope between them is f of X minus f of A all over the difference in the X terms, X minus A. Now, how do we get better estimates of that tangent line? Well, we keep on moving the point closer and closer to A. How do we write that up in symbols? We say, what's the limit as x approaches A? And we call that the derivative of that function at A. Now, you say, why do we need this alternate definition? Well, sometimes algebraically, it works out better if we have this alternate definition. Let's take this for example. We're saying f of x is the square root of x. And I'd like to find out what the derivative function is. Also, I'm going to find out the derivative at A. According to our definition, the limit as x approaches A, again, our definition, f of x minus f of A, is the difference in y values, or the rise, divided by x minus a, the difference in x values, that's the run. And for this particular version, this is square root of x minus the square root of a over x minus a. Now, I can try to apply the limit here. I can replace every occurrence of x with a, but then I get a minus a in the bottom here, which would be a divide by 0. So I really can't do that. Our solution is to do a little bit of algebraic manipulation, and that is I'm going to multiply both the top and the bottom by what's something called the conjugate. Multiplying by the square root of x plus the square root of a over the square root of x plus the square root of a. All right. When I multiply out the top, I get x square root of x times the square root of x, which is x, square root of x times the square root of a, which is the square root of ax, negative square root of a times x, which is negative square root of ax, and then minus a. Now on the bottom, I'm just going to leave this just the way we wrote it in the previous step. All right, break out my red pen because this square root and that square root cancel, which means I now have the limit as x approaches a of x minus a over x minus a times square root of x plus the square root of a. You might see that these two clearly cancel. And now when I apply the limit, it's clear that I just get 1 over square root of a plus the square root of a, or 1 over 2 root a. Let me summarize. If f of x is equal to the square root of x, then f prime of x, the function that gives us the slopes of that curve, is, f prime of x, f prime of a is 1 over 2 root a. Let's do a couple drawings. This function, original function, looks like that. Okay. Let's say here we're at 1, 1. Looking at that tangent line. Do we think the slope of that tangent line looks like 1 over 2 times the square root of 1? I think that looks like a 1/2. It certainly looks plausible to me. What about over here? Let's say at 4. This is the point 4 comma 2. 4 is 1 over 2 times the square root of 4, which is 1/4. Well, certainly that slope did get less steep. My last question is, what about f prime of x? Well, in both of these examples, what did I do with the 1 or the 4? I replaced the a value with the 1 or the 4. So what if x is the thing inside the parenthesis? Yeah, I could just rewrite that as 1 over 2 square root of x. Oh, so even though I use the a definition, I can still rewrite my derivative as a function of x. And no one thinks any the worse of me. Now, we have some different notations for this derivative function that we ought to talk about. So we've been talking about taking the derivative of a function x and getting f prime. But what if we were talking about y equals x squared? What happens when we take the derivative of that? Well, we'll call that y prime. And just say our notation has some flexibility in it. Now, if we note that every time we've been taking the derivatives, we've got rise over run, and we might have thought of the slope as delta y over delta x, rise over run. Well, in the derivative world, we can think of not delta y, but a small change in y. We'll call it dy. Or a small change in x, we'll call it dx. And so dy dx is another way of saying the derivative. So from this example, y is equal to x squared. Y prime is equal to 2x, because that's a problem we did on the previous page. I might also say that dy dx is equal to 2x. And again, that's just another symbol for the derivative. Now, slightly different is this symbol. This is the action of taking a derivative. Think about the difference between what is the square root of 3 and the act of taking the square root of 3. It's like, I'm going to take the derivative of f of x. You know what happens when I take the derivative of f of x? I get f prime, the action of taking a derivative. And so there's our notation. Now, in our book, and having to do with the College Board, we have to be used to the idea that functions may be given to us in many different ways. We call this form, f of x is equal to x squared, we call this an analytical description of a function. But we might also be given the function in the form of a graph. Is that a function? Sure it is. Okay, can we find the derivative of that function? Well, we do something like this. Let's say I want to find the f prime function. Let's look at an x value like 0. And then we ask the question, hey, when x is 0, what is the slope of the tangent line at that point? Well, this graph says, oh, it's 4. So what I'm going to do? I'm going to say f prime of 0 is equal to 4. Well, I can graph that out too. 1, 2, 3, 4. There we go. I've got 1 point on my derivative graph. What about at 1? Well, it says that at 1, that the tangent line slope is 1. So maybe at 1, I can make it a second point. And at 2, looks like the slope is 0. So at 2, how about I put a dot at 0? And at 3, since the slope is -1, so here is me going down to -1. And at 5, another -1. And at 6, it looks like it goes to the 0. And what happens if I connect the dots? Well, I get something that I would say is the f prime curve. And I did it without using a limit at all. Now, it's not perfect, but it's a reasonable estimate. All right. Couple more vocabulary things. All right. When we say a function is differentiable on a closed interval, it means that no matter what point I choose on the interval from A to B, that the derivative exists. It's like, what do you mean the derivative exists? Well, remember, the derivative is based on the idea of a limit. Do all limits exist? No. So does all derivatives exist? No. Now, what about stuff at the endpoints? That point. Can you imagine me trying to walk my secant line point down to get closer to that endpoint when there's no function there? It's like, well, no. Does that mean the derivative doesn't exist at that endpoint? No, it just means that when we walk the point to get closer and closer, it's going to have to come from the negative side. We call that a left-hand derivative. What about this endpoint? Well, there's no function over there, so I can't walk this point closer and closer to that. But I can walk points that are just to the right of it. So if I try to use the limit to get to this point, I might only use a right-hand derivative. It just means I'm restricting which side h can be on. If h can only be negative, I'm going to be to the left-hand side of that point. If h can only be positive, then I'm restricting myself to the right-hand side from that point. Now, what effect does this definition have on some other thing having to do with differentiability? Well, let's think of this particular curve, a piecewise function where y is equal to negative x if x is equal to 0. See, y equals negative x. I know what that curve looks like. It's like that. And how about y is equal to x as long as x is 0 or bigger? Well, that looks like that. Oh, that looks like the absolute value function. Why? Because this is the formal definition of the absolute value function. I'm not so happy with that curve. We can try that one again. Now, I'm going to ask specifically, hey, what do we think about the value of this derivative at 0? Well, let's start talking about the left-hand derivative. Imagine that I'm here at 0, and I'm choosing points to the left, and I say, well, what's the secant line slope there? Well, it looks like -1. Does it matter if I get closer and closer and closer? Meaning my h is getting closer and closer to 0, but is always negative? No. It looks like the left-hand derivative is -1. Or if I wanted to be formal, the limit as h approaches 0 from the negative side of this f of x plus h minus f of x all over h. Let me be a little bit more clear here. Limit as h approaches 0 of when h is slightly negative, and we're interested in only this when, don't mind, come on, eraser, only when x is 0, then we are in the negative part of that piecewise function. Sorry, it shouldn't be negative x. That should be negative h minus 0 over h. Well, that looks like the limit as h approaches 0 from the negative side of negative 1. Okay, well, that's just what we thought it was. The slope was negative 1 as long as we approach from the left-hand side. What happens when we approach from the right-hand side? Well, what's the slope between those two red points? That looks like 1. Does it matter if I get closer? No. Closer? No. It looks like the right-hand derivative is positive 1. What does that look like in symbols? The limit as h approaches 0 from the positive side of f of 0 plus h minus f of 0 all over h. Well, if h is slightly positive, that means this function is in this particular condition, the positive condition. That means I'm going to use that as my functional definition. H approaches 0 from the positive side of h, and then f of 0 is 0, and this is h. Oh, it looks like I've got h over h. That looks like the limit is h approaches 0 of 1, which is 1, which is exactly what we saw. All right, hey, I've got these two limits, one from the left-hand side, one from the right-hand side, and they don't agree. My conclusion is that the overall limit, the limit as h approaches 0 of f of 0 plus h minus f of 0 over h does not exist. Wait, therefore, f prime at 0 does not exist. If the limit doesn't exist, then the derivatives whose definition is based on that limit also does not exist. Let's look at one more example of that type on the next page. All right, and again, we'll do this one a little bit more freely. All right, here's the point that I'm interested in. What's going on at 1? The left-hand derivative says, okay, what's the slope between those two lines? Or those 2 points? Negative 1. What if they come closer? Still negative 1. Closer still? Still negative 1. Closer still? Looks like the left-hand derivative is negative 1. What about the right-hand derivative? Well, let me see. Let me put this right here. Over 1 up 2. Slope between the red point and the blue point looks to be 2. And does that change as my point gets closer and closer to my fixed point? Nope. Does the left-hand derivative equal the right-hand derivative? No, it does not. Therefore, the function's derivative, in this case at 1, does not exist.